Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello everybody, welcome back to another episode of the A-Level Cookbook. Today I'm going to go through a very rapid crash course on Proton NMR spectroscopy and how to tackle a question. So this video is applicable to all exam boards. It's assuming you know the absolute basics like tetramethylsilane, D2O, and so forth. If you don't understand that stuff, go back, have a look, and come back. This is solely just how I work through a question. Right, let's get started. So a chemist isolates compound H from a mixture and sends it for an analysis. The initial analysis shows that the molecular formula is C10H12O. The carbon-13 NMR spectrum shows 8 separate peaks. The proton NMR spectrum of H is shown below. And here we have it. Now, it doesn't mention anything about D2O. I want to check if there's anything about D2O. Reason being is because we add it, and it eliminates either these OH or NH peaks. Because, as you can see, the range at which they cover is across, like, everything. So you can never really tell if a peak is because of this, number one. So it doesn't say that. Now, it says here, key detail, in the HNMR spectrum, the peak of 3.7 would normally be expected at a chemical shift about 1 to the right, at 2.7. So this 3.7 one is actually at 2.7. It says use this information to determine the compound H's structure. So with these kinds of questions, you need to follow a systematic approach. That doesn't mean you follow the same formula, you just collect all the information in a way that makes sense. So what I find a lot of people doing is they jump into doing too many things at once. They find a peak, they do the splitting, they do the, too much in one go. Don't do that. You need to process everything step by step and look at each peak in isolation. So, as with all questions, what you really should try and do is get all the pertinent information separately to the side. Because what people try and do is they try to be Captain Big Nuts and they'll sort of try and just skim back through the question and be like, oh yeah, 8 peaks, and then get it all confused because they just see 8 peaks and they're like, oh, that must be, H is 8 peaks, which is not, right? So it's really important just to go through and extract the information you need and make sense of it in a way that you understand. So I know from the text that the formula is going to be C10H12O. I know that the carbon-13 NMR spectrum has 8 peaks. If that's 8 peaks, that means that there are 8 carbon environments. Before I even touch the datasheet or anything like that, I will always work out the number of environments for carbon and proton. So the proton NMR spectrum environments, well, you can work it out yourself. So there's 1 there, 2 there, 3 there, 4 there, and because these two are kind of separated by a little bit of flatness in between, it's actually 5 and 6. Although, if you're in doubt, just go with what you know. But basically, the entire rule is this helps you work out how many positions you're allowed to mess around with and use. You'll see why in a minute. So I know from this 1, 2, 3, 4, 5, 6 environments, because there's 6 peaks. And writing this down will get you the marks. They want to see your workflow. Lots of people also struggle on putting the thing together in the end. Don't spend ages doing that. If you can't do it within 1 to 2 minutes, just move on. As long as you document every single piece of evidence and thoughts and workflow, it works, and you'll be all right and get at least usually 4-ish. So what I do is I always work through it step by step through each and every peak one by one. So I don't just write a whole load of mishmash and then nothing, as in I literally spell out what I'm doing. So for this one here, don't just write the range as well. Ideally write what the peak usually, roughly sits at. So we have a peak at around, what's that going to be, 1.3-ish ppm, right? Don't dive into the splitting at all. First thing you do is look at what it actually is. So here it's an H to a C with an R group. Now, the other thing as well is that there's a reason these are emboldened, as in they're bold compared to these. The reason they're bold is because they're the ones that cause the peak. Another common example I see with this is, for example, if they get splitting and it says the adjacent carbon has 2 hydrogens, and it was this peak, for example, they'll stick the CH2 there, which is incorrect. It has to be adjacent to the carbon that caused the peak, which is the one with the emboldened hydrogen. So that's why you need to really make sure you follow that rule. You can't just stick hydrogens on for funsies, it has to follow this, and that's why doing each peak in isolation helps. So based on the 1.3, I know it's this, so I'm going to draw it. It seems like extra work, but it makes you not screw up. Cool. So I know it's probably that. Next, I look at the integration, or the relative ratio, whatever you want to call it, and I know it's 3, which suggests there are 3 hydrogens in this environment, as in 3 of these are making that peak. So this now becomes an H, a C, another H, another H. I'm trying to embolden them all, and then the R. Last but not least, you do the splitting. I always leave splitting to the end because it messes everyone up. And when you're writing the splitting stuff, you will say what the pattern is. So here it's a triplet. And then to avoid making mistakes, because people try and jump the gun, say it's a triplet, therefore the adjacent carbon has, and then you cannot possibly mess this up, because I see people say, actually it's a triplet, so there's 5 carbon, 4, wait, 0, no, don't do that. you know that this n+1 rule applies to the thing next to it, so simply just say the adjacent carbon has, and then you know this is a triplet, whatever it is, the number in your head you're thinking of is 2, meaning the adjacent carbon has 2. Because what I also hear people say is, oh, the adjacent is a doublet and this and that. And it's like, no, don't do that. Make your life easier and force yourself to do things in a way that makes sense. So it's a triplet, therefore the adjacent carbon has 2 hydrogens. And then what you do is you draw what this piece looks like. So we've got our H's on our carbon here. And then we now know that this has to have an adjacent carbon as in adjacent to these with 2 hydrogens. So we've got this and something else there. Can't stick a hydrogen on this. I can't put anything there yet. You have to follow what the question's telling you. And the only information I can conclude from this is that this is the piece I have. So the next peak we have is this one at what, like 2.6-ish, I want to say. So there's a peak at 2.6 ppm. And now what we need to do is go look at the range again. Okay, so if I look at this peak at 2.6 ppm, I can see that my options are these 3. Now we know we don't have any nitrogen in this, so out goes that. So it's these 2 left. Now, it's a bit tricky to gauge which of the 2 it is just off the bat. Sometimes in some questions, if you're stuck between this or this, just have a look at the benzene range and see if this peak's there. If there aren't peaks here, then you know it's not that one. Unfortunately for us, there are here, which means it could be either one of these 2. So what you do is you could either just work through both of them and then try and rule them out one way or the other. So if I work on the premise that it's this, so we've got a peak at 2.6, we've got an H there, next to a carbon double bond O in this, remember, because those bold ones are what lead to that environment. Same strategy. So I know that its integration from the graph is 2, therefore it now becomes a C with a carbon here and a carbon there, a C double bond O, and then something, right? And then I know that it's a quartet. Therefore, the adjacent carbon has, well, if it's a quartet, n+1, so remove 1, 3 hydrogens. So what you end up getting is you've got an H here, a C double bond O, a branch coming off of that. And then remember, adjacent means adjacent to this peak that's in bold, as in the one that led to this. So it's not going here, it's going to go there because these are the ones that led to that peak. So you've got a CH3 there. So that could be one piece that we could use. Alternatively, the other piece that comes out of this is a benzene with a carbon and a hydrogen off it. So it could be a benzene, a carbon with a singular hydrogen. If the integration is 2, so it could be this or this, sorry. Integration is 2, you end up with a benzene with a carbon and a hydrogen, and it's a quartet as well. So therefore, this carbon, because this is where the adjacent hydrogens, the hydrogens are, sorry, you would have the adjacent carbon having 3 hydrogens. So the alternative thing this could possibly be is that a CH2 there and then a CH3 there as well. Fine, we'll hold on to these pieces anyway and see what we end up chefing up. Now, let's look at this peak here. So we've got like a peak, or peaks I should say, at 7 ppm, at 7 ppm, oh my god, I can't write. And it's roughly 2 environments here, because remember, this is within benzene, it's 2 separate environments, because you can treat it like that. There's 2 environments, therefore there's 2 substitutions on the benzene, because we know it's from the data sheet above, it was benzene from before. So, and that also adds up because we know its integration is 4, therefore it's C6H4, right? So it's a benzene with 2 H's swapped off, leading to 2 environments. So the swap must be here and here, because then you've got an environment there and an environment there. There you go. So that's one piece. Everything else is hydrogen, these are whatevers. Now, I forgot to do this peak here, so I'm going to go and do that. There's a peak at that with 3.7, but they said it's at 2.7, so we follow that. The peak at 2.7 ppm. So this peak at 2.7 ppm could be, again, this annoying range here, right? So it could be either one of these 2. So if I follow it being that, let's say, so it could be this, double bond O, and then whatever, we know that it's got an integration of 2. So it's going to be an H, a C with an H there as well, sorry, in bold, this and this. And then we know it's a doublet. What's a doublet? Therefore, the adjacent carbon has 1 hydrogen. As in, now it becomes, you've got your piece here that you had, C double bond O and whatever, and the adjacent carbon, as in, not here, not this carbon, the one next to this, right, has 1 hydrogen. So there's a singular hydrogen there and then something else and something else there. Can't put anything else on. Alternatively, if we were to say it's that benzene one, so there's a carbon with a hydrogen. If it's got an integration of 2, that means it's this. And then if it's adjacent carbon only has 1, and then it's a carbon here with only a singular hydrogen and something else there. Again, hold on here. Just don't get too confused. Just stick to your guns. You'll find out eventually what works and what doesn't. Okay, so we've dealt with this peak, this peak, this peak, and this one, or these ones. Now the last one is the one at like 9.7-ish ppm. So 9.7 ppm do the same thing. So we look at our data sheet, what falls in the 9.7 range, that does. So it's going to be something next to a C double bond O and an H, and that's nicely bolded. This is an integration of one, which we would expect if it's an aldehyde. You can't really like add extra hydrogens on here, and that would just complete a molecule. So therefore it stays as C double bond O, and then this, and then it's a triplet. So you'll always say, like I said, the adjacent carbon has, and then you can't screw up this part. So it's a triplet, so the adjacent carbon has two hydrogens. So it's going to be a C, H like that, something else there, C double bond O, and an H there. So we've got an aldehyde group there. Cool. So now what we do is we've got all our pieces. We need to reconvene the basics. So like I said before, we know the formula is this. It's C10H12O. I know I've got 6 hydrogen environments and 6 peaks. Let's just gather up all the pieces we've got. So I've got this, and you may have more pieces than carbons. That's allowed. That you know, the reason being is because they might be other sides of the same bit. We've got that piece. We've got this piece. We've got, sorry, well, it could be this, or it could be, let's just do 2, sorry, this, or it could be, sorry, and then we've also got, so I'm having to remember these. So we've got 2 ores there, and it could be, well, we've got this here with a benzene that's got something and something here. And last but not least, our final piece. So you might be thinking, okay, what the hell was the point of all that, man? You made me do all this effort and use up all this precious penning for what? Well, no, you get your pieces now and you look at what you can construct. So usually what I like to do is I like to either start with the benzene, because that's like nice in the middle, or like if you have a ketone, for example, not this example, but like if you had a ketone, start with that in the middle, or just something that you know is always going to be that way. So usually either middle pieces or end pieces. So I know, for example, this benzene, no matter what I do with it, it has to have 2 substitutions in it, because that's what the Proton NMR spectrum shows. So I'm going to start with that benzene, right? I know that no matter what, it's going to look like that. It has to. The next bit you can start to look at is end pieces. What looks like it's going to go at the end and is not going to possibly change. So here we've got a CH3 on the end of it, and this is a CH2, and this has to be bonded to anything but a hydrogen, meaning that's a pretty reasonable end piece. So we've used up U, we've used up U, because I'm just going to stick that here. So CH and H there, and then a CH3 here. Right? Don't even bother looking at too much detail yet. Just put the pieces roughly together first, and then you can correlate with this later. Cool. Now, let's have a look at what we've got left. I've got 1, 2, and then 3, 4, 5, 6, 7, 8 carbons used up. I've got 2 more carbons left. I've used up no oxygen, so I've still got 1 oxygen left, and then however many hydrogens. Okay, so whatever I need now has to have 2 carbons and an oxygen in. That's a very simplified way of doing it, but it makes sense to me, right? So it's not going to be this, because I've already got like one side with carbons and hydrogens on, although this could be, you know, that could be a C double bond O and an H like this. It's not as obviously like, you know, straightforward to me, so I'm going to just put that to the side. Here, CH3, CH2, I've already dealt with, so it's not that. So this remaining piece is probably something to do with this and this, right? So if we now look at it closely, this one is saying that you have a CH2 next to a carbon that only has 1 hydrogen, and then this CH2 is next to a C double bond O. That's supposed to say or, ignore that. And then whatever's here, right? This one is saying you've got a CH3 next to a CH2 and then a C double bond O. And this one is saying you've got a CHO, like an aldehyde group, next to a CH2 and then something. So again, I need something with 2 carbons. Can't be this, because that's 1, 2, and 3. And also that's like closed off the whole molecule, and that would mean I'm joining a carbon onto another carbon here, like that, which wouldn't work here, because I can't just stick that on there. That's adding 3 extra carbons, so that's also out, actually. So that leaves me with this and this. All you've got to do is just kind of look at what kind of works, really. So like here, this is just 1 extra bond that needs to be used up, and it can't be a hydrogen. Well, I've got 1 bond here that's free. Why not just stick them there like that? So C, H, H, C, double bond O, H like that. Maybe it might not work, but unfortunately this part is kind of trial and erroring. But if you work with that, then you're fine, usually. So then what you do is at the very final stage, you can, or even earlier as well if you feel confident, you just correlate this with how many environments you've got. So here, I know I'm allowed 8 carbon environments, so let's number those. So this carbon's 1, this carbon's 2, that carbon's 3, remember there's a carbon there. This one's 4, this one's identical, that's 4, this one's 5, but this one's also identical, so that's 5, that's 6, that's 7, and that's 8. So our carbon environments are happy. Now let's look at our hydrogen environment. So we've got 6 environments, 6 peaks. So these 3 are all the same, so that's 1 environment. These 2 are the same, so that's 2. There's a hydrogen here, remember? There is no hydrogen there because it's C6H6. One of them's gone now. So there's an H here and there's an H there. So that's 3 and that's 3. This is 4 and that's 4. They're identical. And remember, no hydrogen here. And then we have a fifth one here and here, but they're identical. So 5 and then a 6. So we've matched that as well. There you go. So that's how you do every single one of these ever. You just get all the possible pieces and you just kind of have to look at it. So again, pick a start piece or like a centerpiece or like an end piece, and that usually tends to work. Okay, so here's a second example of me just working through that the workflow as well. Okay, and just for the sake of time, we'll just get told what the, there's an IR spec as well, and just for the sake of time, I'm just going to say what's in it. So the IR spec shows that there is an OH, and there is a C double bond O, suggesting quite strongly that it's a carboxylic acid. Now, same strategy. Number 1, take the overall piece of information in. C10H12O2, that's what we're allowed to work with. Number 2, it's in D2O, D2O, so there is no OH peak. Number 3, how many hydrogen environments? 1, 2, 3, 4, and there's a bit of flatness between them, so 5. So there are 5 hydrogen environments, plus the one that would have appeared from the D2O. So 5 peaks, 5 hydrogen environments, but there's actually 6 hydrogen environments because of that D2O peak hiding the one that's left. Now, what you do is the same thing. So start with this peak at like 1.5. 1.5 ppm correlates to this. So you're going to have an H next to a C and an R. We know that its integration is 3, meaning there's 3 of these environment hydrogens as in the ones in this environment. So it's going to be CH3 and an R. And then we know it's a doublet. So the adjacent carbon has 1 hydrogen. As in now your end piece is this. And whatever. You can't put anything else there. That's all it says. Work with only what it's told you. A lot of people go in thinking, oh, I know it's got to have an oxygen and a thing, and this may be where the CO, like, don't do that. Just stick to what it's telling you first. You can do all of that at the end. Now, next we have a peak at what, like 2.3 ppm? So same strategy. Let's have a look at what that one is. So the options are this or this, no nitrogen, so it's not that. How do we check maybe whether this is present or not? Look to see if there's peaks between 7 and 8, and unfortunately there are. So we can't tell apart them. If there were no peaks here, then we know it's definitely not that. So let's just do both. Screw it. So 2.3 ppm, it's an H next to a C double bond O, and then a something. We know that it's got an integration of 3. So that's suggesting this, right? And then it says it's a singlet. So the adjacent carbon has no hydrogens, but you can't have an adjacent carbon, so it's filled. So therefore, on that basis, it cannot be this. So sometimes if you're stuck on trying to tell which one's which, just try it anyway, and probably run into a barrier like that. So it's probably got to be the other benzene one here. You can be careful to notice that it's a carbon stuck onto the benzene with an H there. So therefore, the one at 2.3 ppm has to be this, CH. Its integration is 3, meaning this. So that bold one now becomes a 3. And we know that it is a singlet. Therefore, the adjacent carbon has 0 hydrogens. Oh, I'm going to write no just so it doesn't look like OH. No H. So if there's no H, well, that adds up because this doesn't have an H on it. So now our final piece there is we have a benzene with a CH3 on it. Next one. So now we have one at what, like 2.6 ppm? What's that possibly going to be? Well, could be you. Could be you. What have we got to lose? Because I've done this, I might give that one a go instead. So H, C, C double bond O, and then something. Remember that that's a hydrogen on a carbon next to this carbon, so that's might be why it looks a bit different. We know it's an integration of 1, therefore it stays as an H, C, C double bond O, and then whatever, right? Nothing else gets added, and then we know it's a quartet. Therefore, the adjacent carbon has 3 hydrogens. So as in the final piece is this H here, and then adjacent to this one, remember, so it's going to be a CH3 here. This can't be a hydrogen, it has to be something else according to this snippet only. C double bond O, and then something. Cool, so that's another piece we have. Last but not least, we've got peaks from from the 7 to 8 range, which is the benzene range, and there's two separations, 2 environments, therefore 2 substitutions. And also, the integration is 4, therefore it's C6H4. If there's 2 environments, 2 substitutions, it means that there's symmetry as well, so I put them there and there. For example, I did it here and here, it would also work, and maybe there and there and there and so forth, but we know it's just 2 substitutions somewhere. So I'm going to put them there and there. Fine, so I know those are the pieces I have. Let's go and reconvene. So the bits and bobs we know. So we know that the entire formula is C10H12O2. I know that it's got an OH, it's got a C double bond O, likely a carboxylic acid. We know that, remember, although this is 5 peaks, it's actually got 6 because that D2O hid them. So 6 hydrogen environments. And then, again, same strategy. Just grab all the bits you've got. So we've got this. So sorry. What else do we have? And we have this. And last but not least, we have this. Cool. So those are all our pieces. Same strategy. Pick something that looks either central or something that's like, an end piece or something is not going to change. So I know that can't possibly change. It's the only piece, there's no debate about it, and like assuming you follow the steps, right, that can't possibly be anything else. And I know this benzene's only allowed 2 substitutions too. So I'm going to put the benzene in the middle. I'm going to put them here. And then I know that that's done and that's done because there's a CH3 there. No doubt about it. The remaining bit now. So look at what you've got and reconvene. So we've used up 7 carbons. So 1, 2, 3, 4, 5, 6, 7. So I've got 3 left. So 3 carbons are left. Hydrogens, you can count them if you want, but whatever, I've got 2 oxygens left as well. So I need to squeeze on 3 more carbons on this somehow and 2 more oxygens. Also, you can look at how many environments you've used up as well if you want. So we have 6 environments in total. Well, this CH3, all 3 of them are in the same. So I've used up 1 here. There's an H and an H here, but they're both identical. So I've got a second one here and a second one there. These 2 as well, same problem. So 3 and 3. So I've got 3 hydrogen environments left. Fine. So now all I do is I just put together what I can using the remaining pieces. So if we observe carefully, we need to make sure that we've got 2 oxygens. Remember, one of them is going to come from the OH anyway, so that addresses that. And I need to make sure we put 3 carbons on. If we look at the pieces we have remaining, a CH3 next to a carbon and only 1 hydrogen, and then 2 other mysterious things. If you look here, 3 hydrogens, a carbon with 1 hydrogen. That matches this, doesn't it? And then also 2 other mysterious things. Well, something there and something there. Here and here match, and then there and there match. So sometimes you find that the molecules you end up with are same sides or similar sides of this, bits of the same thing. So one of these bonds, what's to stop me from saying, okay, well, one of them goes on this benzene here. The remaining thing that's left is this C double bond O. So that's the piece, isn't it? So you've got this carbon with 1 hydrogen and then the CH3 here, right? And then that satisfies this part, and this part's satisfied as well because it's bonded to this carbon here with no hydrogens on, remember, the benzene doesn't have it anymore. And then all that's left is this carbon with a double bond O, which I can stick here. And then I've got that OH that was removed from the D2O, which is this. Boom. Now what you do is you count up the remaining environments as well. So we have 6 hydrogen environments. How many hydrogens we got left? Well, we've got 1 here. So that's what? So 4. These are all identical. So 5, 5, and 5. And then 6. Boom. It adds up. Everything's there, done and dusted, finito. So that's how you do every single one of these questions ever, in my opinion. If you can't work out the structure, just leave it and move on. Like, as long as you do all of those steps, you can secure a pretty decent amount of marks, to be honest. I hope that helps. Thank you very much. I do feel a bit bad that I'm not able to do the papers. It's just because this year's been quite busy and a bit tough. Lots of deadlines, lots of bits and bobs going on. But I appreciate all of your support and I hope everything's been going okay. Thanks.